In this problem, there is an unknown polynomial q of x of degree 2. We are given 3 points that lie on q of x. Call them P1, P2, and P3. We are also given one bogus point, P4, that does not lie on q of x. The question asks us if we can use the machine that we developed in part 1.4 to figure out which point is the bogus point. It turns out that no matter what order we pass in the 4 points into our machine will always output no. Therefore, there is no way to figure out which point is the bogus point. We can prove this by splitting this up into 2 cases. In the first case, the first 3 points that we pass into the machine are the correct points. Thus, the 4th point is incorrect. In this case, the interpolating polynomial will simply be q of x. When we evaluate q of x at P4, we'll see that P4 does not lie on q of x. Therefore, our machine will output no. In the second case, the incorrect point will be one of the first 3 points. In this case, the interpolating polynomial will be some polynomial q prime of x, which is not equal to q of x. Thus, when we plug in one of the correct points into q prime of x, we will see that it does not lie on q prime of x. Therefore, our machine will output no. In this problem, we're given 5 points, one of which is incorrect. Now we can use our machine to figure out which one is the liar by trying out all possible combinations of 4 points. If the 4 points that we choose contain the incorrect point, then as we saw in the previous part, our machine will always output no. If, however, we pick all 4 of the correct points, then our machine will output yes. This means that the missing point must be the incorrect point. Using what we have learned from the previous 2 parts, we consider all possible combinations of d plus 2 points. Now, if our d plus 2 points contains the incorrect point, then there does not exist a polynomial of degree at most d through those d plus 2 points, and therefore our machine will output no. Otherwise, if our d plus 2 points are all correct, then there does exist a degree d polynomial through those d plus 2 points, and therefore our machine will output yes. In this case, we know that the point that was left out must be the incorrect point. So now let's work out an example where d equals 1. If we plot the 4 points given, we get 1, 3, 2, 2, 3, 2, and 4, 0. Now let's consider all possible combinations of 3 points. So the first combination is 1, 3, 2, 2, and 3, 2. We interpolate using the first 2 points and then see if the third point lies on the interpolating line. So we can use the point slope formula for a line to figure out the interpolating polynomial. In this case, the slope is 2 minus 3 over 2 minus 1, which is negative 1. This gives us the equation and simplifying yields y is equal to negative x plus 4. Now we plug in this third point, so we get negative 3 plus 4, which is equal to 1, which is not equal to 2. Therefore, our machine outputs no. Now moving on to the next combination, 1, 3, 2, 2, and 4, 0. Again, we interpolate using the first 2 points. Since these first 2 points are the same as the first 2 points in the previous part, we get the same equation. So y is equal to negative x plus 4. Now plugging in 4 for x, we get negative 4 plus 4, which is equal to 0. Thus we have that these 3 points all lie on a line. Therefore, we can conclude that the point that was left out, which is 3, 2, must be the incorrect point. And we can see that clearly from our picture. Given D, there are D plus 3 points. This means that there are D plus 3 combinations of D plus 2 points. Then using the algorithm developed in the previous sections, we see that it is sufficient to run the machine on all D plus 3 combinations. However, we can do slightly better than this since we know that there is exactly one liar. If we run the machine on D plus 2 distinct combinations and the machine outputs no every single time, then we know that the final combination must be the one without the liar. Thus, in the worst case, we only need to run the machine D plus 2 times.